Momentum, much like energy before this, is a conserved quantity. So that means that the total amount of momentum within a system is going to stay constant. So let's look at a quick example of what that might look like. Let's take the example of two cars moving along. We have car 1 with mass m moving at a speed v1, so m1 v1 would be momentum 1. m2 v2 would be momentum 2, and if you added those together, that would be the total momentum of our system before anything happens. Let's go ahead and assume that velocity 1 is greater than velocity 2, so that means this car is eventually going to catch this white car, and if it would keep at that speed, which we're going to assume it does, it's going to collide with that car. So in the after situation, kind of what we would expect happens. We have our mass and velocity for objects 1 and 2. But this time mass 1 is traveling a little bit slower after the collision, but mass 2, because it got hit from behind here, is going to be going a little bit faster. But if you took m1 v1 plus m2 v2, so momentum 1 plus momentum 2, you'd still get the exact same total amount of momentum that you had before. One kind of critical assumption that we're making here is that when we choose our system, right, this black box, circle-ish box here, represents our system of interest. And it says here that net force equals 0. In other words, there are no forces acting on any of these things outside of this system. That's a condition that we need in order for conservation of momentum to hold true. But it's a pretty common occurrence and something you won't have to think about too much. Mathematically, conservation of momentum looks something like this. Let's consider our impulse momentum equation. So P1 equals force 1 times T. And change in momentum for object 2 involved in a collision would be force 2 times time. So maybe think of this as the first car and the second car in the previous example. We know from Newton's third law that the force that car 1 applies to car 2 is exactly opposite of the force that car 2 applies back on car 1. So we know those forces are equal and opposite. So if we look at what that means in terms of momentum, that means my change in momentum 1 plus my change in momentum 2 is going to be equal to 0. And that's kind of an important thing. That means that the total momentum in the system doesn't change. We can make sense of this, right? F1 would be some value, let's maybe say 10. F2 would be negative 10. Times, let's say they collided for a second, so that's 10 kilogram meters per second here, negative 10 kilogram meters per second here, so 10 plus negative 10 would give us 0. So no change in momentum overall. So we can write this one of two ways. We can say that momentum 1 plus momentum 2 initially equals momentum 1 prime plus momentum 2 prime. So the prime here, this little asterisk here that we use as prime apostrophe, represents what's happening after, and this is what's happening before. Or we can simply say, if maybe there's more than two objects involved even, that just total momentum before equals my total momentum afterwards. And that's what conservation of momentum is going to be mathematically when we go to solve a problem. So let's look at an example here. We have a 0.4 kilogram ball that strikes a 0.2 kilogram ball that is at rest with a speed of 3 meters per second. And then we're saying that the 0.4 kilogram ball is moving at a speed of 0.5 meters per second after the collision. What is the speed of the 0.2 kilogram ball? So we have that momentum 1 plus momentum 2 equals momentum 1 prime plus momentum 2 prime. So momentum for object 1 is mass 1, velocity 1 plus mass 2, velocity 2 equals mass 1, velocity 1 prime plus mass 2, velocity 2 prime. Notice I haven't put primes on the mass part of this. That's because we're assuming that mass is not going to change in these collisions. Well, the 0.2 kilogram ball, we'll call that object 2, is at rest. So that means its initial momentum is 0 because it has 0 velocity. So let's go ahead and plug in our values now. 0.4 kilograms for our ball initially moving at 3 meters per second equals our 0.4 kilogram ball again, moving at 0.5 meters per second, plus our 0.2 kilogram ball, moving at whatever v2 prime is, which is what we're looking for. So if we go ahead and solve this, we're going to take our 0.4 times 3 minus our 0.4 times 0.5. And when I do that, I get 1 kilogram meter per second equals 0.2 kilograms times v2 prime. So to solve for v2 prime, we're going to take 1 divided by 0.2, which is 5 meters per second. And that would be our final answer. Now, one important thing to note here is that direction is going to play a very important role in momentum. We weren't very specific in this problem, and we didn't say that this 0.5 meters was in the same direction as its original 3 meter per second velocity. We just kind of assumed that. It is possible in a collision that, say, object number 1 might be moving backwards after the collision. In that case, we would have to replace this 0.5. Let's say it was moving backwards at 0.5. We'd replace this 0.5 with a negative 0.5. So being very careful with positive and negative velocities in terms of direction is going to be very important when it comes to solving problems, and something you need to pay extra close attention to.